Being able to identify minerals is a very valuable skill, and that's why I'm putting together this master class of how you can learn to identify minerals for yourself. I mean, it'll help you, and you'll be miles ahead if you're prospecting or looking for different kinds of rocks or crystals, because oftentimes there are indicator minerals and rocks that will tell you, oh, you're close by, or you're almost there, or this is the direction you need to proceed. And if you can't identify those, you're kind of lost. But if you can recognize those minerals, you can be miles ahead of other people. And sometimes the things you find, sometimes stuff you find can be valuable. You find a beautiful clear crystal. Is it a diamond? Is it a piece of quartz? What is it? And it can tell you how valuable interesting finds that you make are. It's a skill that's really valuable, and it's a skill that most people aren't that really good at identifying minerals. And so I put together this master class. So watch with me, and you will have that skill. If you come to the end, if you stick with it, you will have that skill of learning to identify minerals, and you'll be glad you did. Hey, I'm Chris Ralph, the professional prospector, and today we're going to talk a little bit about mineral identification. Now, I get emails every day, people telling me, hey, how can I send you some pictures? Because I found some kind of rock and I want you to tell me what it is. Sometimes I think it might be gold, or I think it might be diamonds or platinum or some other thing. And I get so many of those every day that I tell people I can't do that. First of all, it's way harder than you might think to look at a picture and just say, oh yeah, it's a such and so mineral. And if I was doing that every day, I'd be spending an hour a day looking at people's pictures. So I'm sorry, I can't offer that service. I tell people, if you really don't know, have somebody local look at it for you. But what I'm going to do today is we're going to talk about the techniques, how you can master learning to identify minerals. And you can have a skill of what you need to know to learn to identify minerals. Now, we're going to talk about mineral identification and all the different characteristics that you need to get into to be able to know what a mineral is. And first off, we talk about crystal shape. And I got an example here of a crystal, and it has a characteristic kind of shape. If you knew about minerals, you would look at this crystal closely and be able to tell it's a quartz crystal. This is actually a large quartz crystal I found when I was prospecting for gold in Australia. But it's a really cool specimen, and I brought it home because, well, it was just a lot of fun to find it. But quartz crystal, right? And crystal shape for quartz crystals is really good at helping to identify what they are. Hardness. We'll talk about hardness. Every mineral has a certain level of hardness. Quartz happens to be hardness number 7 on the Mohs scale, which goes from 1 to 10. But we'll talk about all those different ones, and we'll look at different possibilities when we talk about hardness in more detail. Cleavage. A number of minerals tend to break in a certain shape. Here's one right here. I don't know if you can see that very well, but it's a fragment. This isn't actually a crystal that didn't grow this way. It actually broke. It was broken on purpose. Somebody did this, with a sharp edge. You can hit the crystal and it will naturally break in certain fracture ways. And the ways that the crystals break are identification to tell you what this crystal is. Okay? And then we get to color. Now, I want to show you, here's a clear crystal. It's actually a cleavage fragment like this other one. Here's the crystal fragment, the cleavage fragment I showed you just a minute ago. And here's my quartz crystal. Now, these are all 3 colorless minerals, right? They're minerals that are clear. And that's their color, is clear. And if you were to do a streak, we'll talk about streak tests. If you were to do a streak, it would be a white streak for all 3 of these. And yet these are 3 different minerals. That's why I say you send me a picture and I can see the color of whatever it is you found. And yet the same color can be three different minerals. And in fact, all of these minerals come in different colors other than clear. Quartz can be a number of different colors, purple and yellow and reddish and green and a number of different colors, brown. This mineral is calcite, and it can come in a wide variety of colors, greens and reds and a lot of different colors. And this mineral is gypsum. It also comes in a number of different colors. So just having color is actually the weakest and most worthless of all the characteristics that you can use to identify a mineral. And so when people say, hey, I want to send you a picture, it's like, you're going to send me one thing to figure out what a mineral is, and it's the most worthless thing, the color. Because there's a lot of minerals that actually occur in every color of the rainbow. Yellow, blue, red, green, purple, orange, you name it. They come in whatever color you want them to be in, okay? And we're going to take a look at that too. Luster, that's some minerals have a kind of a pearly look, or they look greasy or oily. That's called an adamantine luster. We'll take a look at those things. Magnetic properties. Some minerals are magnetic. You can put a magnet to them and the magnet will stick. That tells you a lot about a mineral. And then various chemistry and chemical tests. This particular mineral, the calcite, if you put a drop of dilute hydrochloric acid on it, it will start to fizz and bubble, because calcite is calcium carbonate. You put acid on a carbonate and it starts to bubble, just like the fizz in a carbonated drink like Coke or 7-Up or something like that. So there's a lot of different chemical tests that you can do to test for the presence of different elements or different types of chemistry. So those are also sometimes used to distinguish between minerals. So let's get into the skills that you need to find out what a mineral is. Oh, and one more thing I want to go to is, you may say, well, I can't remember all the crystal shapes and hardnesses and cleavage and color, luster, all these different properties. How am I going to remember all that stuff? Well, okay, this is what I recommend. I recommend that you buy a book about rocks and minerals. These books, this one is a particular one by Simon & Schuster, but there's a lot of different ones on the market. You can find them on Amazon. I even have a little bit about this kind of stuff in my book, but there are books that specialize in helping you to remember all the different properties of the crystal shapes and hardness and that sort of thing, so that you can identify minerals. But we're going to delve right now into taking a look at some examples of different minerals and some things about how you test the hardness and the crystal shape and identify that kind of stuff. So come along with me and we're going to delve right into that right now. So let's talk about the skills that are necessary to be able to identify minerals in the field. You know, it really is a skill, just like, you know, learning a trade or something like that, to be able to look at minerals and have a pretty good idea what they are. Now, there are, you know, one of the things about identifying minerals in the field is that it's more difficult than you probably imagine that it is. Just like, you know, when you see a plumber or an electrician doing what they do, you know, it looks easy, but it probably takes a lot more knowledge than you would expect. The same thing with identifying minerals. Weathering is something that makes it a lot more difficult. I'm going to show you a picture here, and take a look at this, and you can see there's three different rocks here. Believe it or not, all three of these rocks are exactly the same kind of rock. And they were all found fairly close to each other, within a few hundred feet of each other. The lowermost one in the lower right, that's silver gray colored, is what the rock looks like unweathered. In other words, the effect of rain and water for a long, long time hasn't changed it very much. It's been protected. So that's what it looks like, what the rock looks like. The rock that's more in the middle on the left, that rock with the kind of purplish color, it's been weathered a moderate amount. And it changes the hardness and other characteristics of the minerals in that rock. And then the rock on the top, on the upper right hand, it's the same rock too. It's just been even more weathered. So you can see that Weathering can change a mineral in a very large way and make it much harder to identify. Weathering can convert minerals to clays and other sorts of things, and it makes it harder to tell what they are. Here's an example of a mineral that's been pretty wildly weathered. You can see it's dark brown, kind of black. Well, this is a piece of pyrite. Pyrite is yellow and metallic looking. This is not metallic looking, and it's definitely not yellow. So what's the deal with this? Well, this piece of pyrite has been exposed to the wind and the weather, not necessarily on the surface, but near the surface, and it's changed the pyrite into limonite or goethite. This is an iron oxide mineral. So the iron sulfide of pyrite has become iron oxide of other minerals. And it changes the hardness, it changes the color and the appearance, but probably if you broke this open, you would see on the inside some of the nice yellow metallic looking pyrite that it originally was. This is called a pseudomorph. It's a false form. So on the outside, it's iron oxides, but it has the form of an iron sulfide pyrite. So, weathering can even make what's called pseudomorphs, a false form. You can see too that weathering changed the color of that little specimen. And that's part of why I say that colors are rarely characteristic. Crystal shapes are an important part of identifying minerals, and sometimes in the field, pieces are broken or they're kind of lumpy looking, and they've been, changed by weathering, and so you lose a lot of times that ability to identify the crystal shape. Sometimes there are families of minerals that are closely related. This is a specimen of garnet. And garnet forms a family of minerals. There's a number of different minerals that are considered to be garnets, but they're a similar chemical makeup and a similar crystal shape. And so because they are so similar, it's called a family, and the family is called garnet. But there are individual minerals like grossular garnet or andradite, or there's various other different garnet minerals, and it sometimes can be hard to separate different minerals in the same family because they have the same crystal shape and a similar chemical and often a similar density and other factors too. So it can be tough to separate minerals in the same family. Another thing that's worth knowing is common associations. A lot of times when you're in a certain geologic environment, it's normal to see certain kinds of things. So if you're in one type of environment and several minerals are pretty common in that sort of environment, then you will expect to see, you'll have in your mind, this is a pegmatite, and so I might expect to see tourmaline or mica or some other kinds of minerals. That's pretty normal for pegmatite types of deposits. So knowing those frequent associations, that's another thing that's helpful in identifying minerals. So field identification of minerals, it often can be done, but it's not always easy. It can be pretty tough to identify a mineral in a field. You may need to take it home and do some testing with it and figure out what the mineral is after maybe consulting a book or something like that. You may need to consult a reference to figure out what a mineral is. Like I say, it's not always easy. But what makes a difference. Like I say, it's like a trade skill. What you learn and what you know make a huge difference in your ability to identify minerals. And like I say, it's not always easy. Different minerals have different characteristics. Sometimes you need to consult a reference to be able to figure out what it is and know what kind of mineral you have. But like I say, there are different skills and things that you can use to help identify minerals. And we're going to take a look at some different ones right now and kind of give you some examples. I talked about a little bit about these different categories of things that you can use to identify minerals earlier in this video. We're going to talk about it in more detail now. But what I want you to see with all these different characteristics like hardness, crystal shape, density, all these other things, is that it's kind of like the game show Wheel of Fortune. Have you guys ever watched that, or at least seen what it is? They have a board with a bunch of spots on the board, and it spells out a word or phrase or saying or something like that, and the contestants guess one or two letters at a time, and the game, they fill in the letters. So if somebody says, well, I'd like to see if there's a C in this saying, and the C's will appear if there is. And so what normally happens is a few letters will appear, and then a few more letters, and a few more letters, and eventually it becomes really obvious what the phrase is, because you may eventually have most of the letters there and only be missing a few. And that's kind of what identifying a mineral is like. So you get the crystal shape, but a lot of times crystal shape by itself isn't going to tell you, but then the hardness, and then the color, and then the density, and then something else. And you put all these things together, and it's like being on Wheel of Fortune and having all the letters filled in, or almost all the letters. And then you can look and say, oh yeah, it's a feldspar, or you'll say the saying that that the Wheel of Fortune has. So that's how I want you guys to think of these different categories, that they each provide another clue as to what the mineral is, and when you add them all together, then you're going to get the answer correctly. You're going to know what the answer is as to what kind of mineral it is you're looking at. So let's take a look at these right now. We'll go through these categories each individually, and I'll kind of demonstrate them out for you. Okay, so now we're going to talk in more detail about our mineral identification clues, and we're going to start off with crystal shape. Now that's certainly one that's usually recognizable when you can see the crystal, and there's a lot of different ones, but there's only so many shapes. All the shapes are symmetrical. In other words, you can't have a 7-faced crystal or a 5-faced crystal, because that's not symmetrical. But you can have a 4 or a 6 or an 8. So just to let you know about that. Now, this is a piece of quartz, and quartz has a 6-sided crystal shape. Whoop. But this is a piece of beryl, aquamarine, and it also has a 6-sided crystal shape. So one of the things that's important to note about crystal shapes is there's only so many of them. This one is fluorite, and it has a cubic crystal shape. But I noted to you, this is pyrite, or was a pyrite crystal, and it has a cubic crystal shape also. Table salt, halite, the mineral that makes for regular table salt, also has a cubic structure. But all of these crystals a lot of times will have modifications that'll help tell you about them. One of those is striations. Now on quartz crystals, a lot of times you have the crystal growing a longer axis, and along the crystal faces, there'll be striations that you can see. This one, you have to kind of hold it in the light and reflect off it to be able to see the lines. But you can see it, and that's kind of a characteristic thing where you get the crystal shape with a point, and you can see the lines along the crystal. That marks you for quartz. Whereas notice that the top of the beryl crystal is flat, and then you have the sides. And if you look at this reflection of the sides in the light, there are no horizontal striations. That's one way that you could tell a clear colorless beryl crystal from a colorless quartz crystal. Pyrite is another mineral that often has striations along the crystal face. And the other thing too is that some crystals will grow in what they call modifications of a crystal. So you'll see like pyrite, most of the time it's cubic, but sometimes it has octahedral or other sorts of modified cube types of shapes. And this one is fluorite, I mentioned. Well, this green is also fluorite, but this cube, I don't know if you can see it, is kind of a diamond shape. It's octahedral. This is fluorite. It's cubic, but they're the same. So sometimes the crystals are modifications of one form or another, and it may not be as obvious, but knowing more about crystals and crystal shape will help you know that. So let's move on to our next clue in our wheel of fortune of figuring out what minerals are. The next clue that will give us a few more letters in the phrase. So our next clue is hardness, and all minerals have a certain hardness, and you can test them by making a scratch or seeing if you can make a scratch. And what you do with that is you have a known set of minerals, and then you do a scratch with that mineral. And if mineral number one will scratch, you're trying to identify a mineral, right? And so you do a test on the mineral you're identifying, and if quartz will scratch it, then you know it's at least as hard as quartz. If quartz won't scratch it, then you know it's harder than the quartz. And then you keep on moving up or down to figure out what it is. So this is a test kit. I'll kind of move it in here. You can buy mineral test kits on Amazon. There's a number of them that range from fairly inexpensive to super expensive. They have different kinds of things. But this is a range where hardness 1, hardness 2, hardness 3, hardness 4, 5, 6, 7, 8, 9. There is no diamond in there to test, which is hardness 10. But this is actually corundum, which is the mineral. This is corundum. That's the mineral that the rubies and sapphires are made out of, and it's hardness 9. And then topaz, quartz, feldspar, apatite, fluorite, calcite. Anyway, there's all of these together that you can use to test for hardness. And finding out the hardness of your mineral that you're trying to identify, finding out the hardness will tell you more information about what the mineral might be and give you a clue that will help you find out what mineral you have. Now, one thing with hardness is that you got to remember, as I talked about a few minutes ago, that weathering can change a mineral and change the hardness. I keep bringing back this piece of iron oxide, limonite, goethite, that was once a piece of pyrite. If you test this, it won't test hardness for pyrite because it's weathered. So that's one of the things you need to know about testing hardness. You need to test minerals that are not weathered or changed or altered in any way. Because then you're testing, other things about the mineral. So hardness. Okay, so number 3 is density. And some minerals are a lot heavier than others, just a lot more dense. This mineral is galena. It's from a mine that produced lead ore. And because of the lead, the density of galena is real heavy. And unfortunately, I can't show you on a video that something is heavy, but it is. Now, I showed you this quartz crystal. There's a lot of minerals that are in this range, pretty close to what quartz is, but there's not as many that are super heavy. And so having a high density tells you that it belongs to a certain group. And now I can just heft this and say, yep, it's pretty heavy. But if you want to actually know what the density is, because there are tables of minerals, like I say that my rock and mineral book will tell you what the density of that mineral is supposed to be. If you're thinking, well, this might be stibnite or some other mineral, right? You can test the density, and it will tell you in the book what the density of stibnite or whatever other mineral you're looking at, what the density is supposed to be, or galena. Now, density is figured with a water test, and I'm going to show you a little bit about that right now.
The calculation of density is basically weight over volume. So it's often calculated as grams per cubic centimeter. And it's basically a weight type of thing. It's easy enough to weigh an object or a mineral dry and see how much the weight is. But then calculating the volume is a little more difficult. Here is a picture of a piece of quartz that has gold in it. You can't actually see the gold in the picture, but it actually has quite a bit of gold in it. It's suspended in the water. The quartz isn't actually touching the bottom of the little cup, and it's being weighed in the water, submerged, but not touching the bottom. And that actually is the difference between that and the weight of the water without the specimen in it, is what's used to figure the volume. Anyway, it's an important thing, and it isn't always necessary to calculate the exact density out, but it's something that can be very helpful in identifying a mineral.
Okay, let's talk about our next mineral identification clue, which is cleavage. Now, cleavage actually is one of the things that are the most useful for identifying a mineral, if a mineral has cleavage. Not every mineral does, but when it does, a lot of times that's very useful to help you in identifying what the mineral is. I'm going to show you this again. This is a fragment. You can see it's kind of a tilted rectangle. This is a piece of calcite, which is a mineral, and it has 3 separate cleavages. There's 2 cleavages there, 2 cleavages there, and one in the cleavage here. So a pair. So each of the pairs is 1 cleavage. So there's 3 cleavages because there's 1. Whoop, because there's 1, 2, 3 separate faces of cleaving. And what it is basically you can take a sharp edge like a razor blade or knife edge or something like that and put it on the mineral and whack it with a hammer, and the mineral will break along a certain plane. That's what cleavage is. And if a mineral has, like I say, cleavage, it can identify it because the actual angle of these breaks, so like on calcite, this angle between all the different planes, yeah, that angle is always the same. So if you were to look at any calcite crystal or break it or whatever, it would always have the same angles between the faces of the cleavage. It has to do with how the atoms are arranged inside the crystal. There's points or planes of weakness, and the planes of weakness between the atoms is what makes for cleavage. Now, some of you may have seen like pictures or heard about people breaking diamonds. You know, it's a very careful way where they put a knife edge and then hit it with a mallet. And that's what they're doing. They're cleaving diamond. That's how, one of the ways that they break a diamond up, if it has flaws in it or cracks, they get it set up for cutting. They don't do that with small diamonds, but with the big, super, valuable ones, 20 and 50 and even more carat rough pieces of diamond, they will cleave it to organize the crystal into its most useful shapes, and so that they can get the most valuable stones out of it. Now, sometimes there is a few minerals, the number of cleavages, you can have 1, 2, 3. 3 gives you a full 3-dimensional shape, but there are some minerals that have even more than that. This mineral over here on this side, there's actually 2 minerals. One on this side that's gray, and another one on this side that's brown. The brown one is a mineral called sphalerite, and sphalerite actually has 6 different planes of cleavage. As far as I know, it's the only mineral that has that many planes of cleavage. The other mineral on the other side breaks to square shapes and is gray and is heavy. And so by putting together gray, heavy, square, it's galena. And then, I told you knowing associations will very commonly sphalerite, which is a zinc ore, and galena, which is a lead ore, very commonly sphalerite and galena are found together. So here you have a perfect example of just that, knowing the association, knowing the color, knowing the cleavage, knowing the density. You put that all together and you've identified the minerals. And then on the back, there's a light color thing, which if you look around on this piece, you can see the cleavages on it too. White colored cleavage. And we're going to talk about another test, which is an acid test. You can put a drop of acid on this mineral and it will fizz, and that identifies it as calcite, which is the same mineral as I showed you a second ago. This also is calcite. Okay, so cleavage can be a really helpful and useful tool. And here's a mineral that has a silvery gray color, kind of like the galena, but it only has one cleavage, and it's one very easy cleavage, even to the point where when you touch the mineral like this, it feels slippery because the basically it's cleaving off little fragments of the crystal as you're rubbing it. That's why it feels slippery. And so this mineral, because it only has one cleavage, so it can't be galena, which has three cleavages that are in a cubic shape. They're all at right angles to each other. So it's not galena. It only has one cleavage, and galena's cleavage is not so perfect that you just rub it and it feels slippery. And actually, if you rub this on your finger enough, your finger will be darkened, just like rubbing pencil lead on it. But it's not graphite either. And graphite actually can be silvery and has a single cleavage like this. But the trick is this mineral has some significant density to it. And unlike graphite, which is really light, graphite is what they use in pencil lead. This mineral is a little heavier. It's molybdenum. It's the ore of molybdenum. Molybdite is the mineral. Molybdenum is the metal that comes out of this ore. And it's actually used, they take that molybdite because it's, like I say, greasy and stuff. They actually put it in greases, and it makes it a high temperature grease that will lubricate things at a fairly high temperature. So if you've ever seen molybdenum or molybdite grease, this is what it has in it. It's a mineral that makes it a better lubricant because, like I say, it cleaves so easily. It's slippery. Another mineral with a single cleavage is this mineral. You can see it's kind of silvery. This mineral breaks. I don't want to break it any more than I have to. But even as I rub it, little pieces, I don't know if you can see it, but little pieces are slipping off and falling on the floor. This mineral has one very perfect cleavage, and if you look at it on the edge, it looks silvery. But if you turn it this way, it looks, here's one that's on edge. It looks like a book. I mean, there's a whole bunch of little flat pieces all together, just like the edge of a book. And this kind of has that, you can see. But anyway, this mineral is mica. It has one perfect cleavage. And it is something, because this is an example that's silvery. There are some that are kind of golden in color. And there are people that find this kind of golden color material, and it has a kind of a metallic sheen look to it. They don't think about the edge on view. They just say, I see yellow and metallic. It must be gold. Well, it's not. And actually, mica is a very common rock-forming mineral, and it's not unusual that it has a golden kind of color. But if you turn it on edge and it's no longer golden, it looks like a book or something like that, yeah, it's mica. And actually, they call crystals of mica books of mica. That's a term that geologists use. He found a book of mica, and that's what these are. These crystals are books of mica. Now you can use a little bit of color to help separate. Remember I said there are families of minerals? Well, like garnets, where there's a number of garnet minerals, there are a number of mica minerals. And this mica, which is silvery or light colored, is going to be muscovite. But here's a one that's got the same mica type of structure, and the edge on it looks like a book, but it has a light purple lavender kind of color. And it's found in pegmatites. And if you put light purple, lavender, mica, pegmatite, that association with pegmatites, then you put that all together and it's a mica family mineral called lepidolite, as opposed to this silvery one that's called muscovite. And like I say, there's associations of minerals. This is actually a specimen not of mica, but it's intended to be a specimen of aquamarine. This light blue color crystal is aquamarine beryl, and the white next to it is feldspar. So this is a feldspar crystal. But they grow in big crystals like this. This is how pegmatites grow, is big crystals like this. So that's another thing about, you could use cleavage together with other things, color and other appearances, to identify a mineral. Okay, we're finally going to get to the mineral identification clue, color. Okay, and as I said before in this video, color is the most useless and worthless of all the clues. Because generally speaking, a lot of minerals come in different colors. And there are lots of minerals. Well, first of all, there's minerals that come in every color of the rainbow. And then there's colors that have hundreds, if not thousands of minerals. The color, dark color, black or near black. I found a black mineral. What is it? Well, it could be about one of about 500 or 1,000 different minerals. And just from the color black, I have no idea which of the 500 minerals or 1,000 that it might be. So sending me a picture of a mineral that's black, I don't know. Send me a picture of a mineral that's red. There's hundreds of minerals that are reddish. And so, or brownish or yellowish, it's just not a very useful kind of thing. But you can put it together with other stuff, like I showed you a second ago with the lepidolite and the muscovite, mica. You could see that it was a mica by looking at the cleavage and how it's set up. And then you could see the color, know the association that was found in a pegmatite, and you could know that it was lepidolite mica. And lepidolite actually is an ore of lithium. Lithium batteries and stuff like that. Yeah, a certain amount of the lithium mined in the world comes from the mineral lepidolite. It's mined out of pegmatites. There's several lithium minerals that are found in pegmatites, spodumene and a few others. But in any case, that you can color together with other things. I mentioned garnet as a family. You can't separate garnets based on color because a lot of garnets come in various shades of red, purple, brown, yellow, all kinds of things, orange, green. There's green garnets. Actually, there's emerald green garnets, and they're considered quite valuable. Like I say, there's some minerals that come in virtually every color of the rainbow. This is a specimen of tourmaline. It's dark green. This is a specimen of tourmaline. It's a lighter green. This is a specimen of tourmaline. It's pink. This is a specimen of tourmaline. It's black and opaque. But there's tourmalines in every color. I have tourmalines that are yellow, purple, orange, brown. I even have a specimen of tourmaline that's essentially colorless. It's super pale pink. If you put it on a piece of white paper, you can barely see that it's a slight pink. If you just hold it in your hand, you would say it was colorless. So minerals can come in a variety of different colors, and color is probably the least helpful of all the different clues that you can get. So when you send me a picture, and like I say, I don't want you to send me pictures. If you send me your pictures, I'll probably just erase them. All I can really see is the color. And like I say, it's the most useless of the clues. So color, again, it can be combined with other things, and you can look at it, but you know, with just color alone, which is really pretty much all you get with a picture, it's hard to tell anything about it. So that's color. I wish I could tell you color was the best clue, but it's not. It's the least useful. Sometimes color is useful. I will show you this. This is a kind of a dark blue color. And so if you're in an area that you know has copper minerals, so you have an association link, and you see this really dark blue, it's pretty high odds that it's azurite. This is a common copper mineral. It's a copper carbonate, and it is an ore of copper. And you know, it can, so color in that case, because you also have an association, is useful for identifying a certain mineral. So our next mineral clue is luster. And again, this is a mineral characteristic that's not always all that useful, though sometimes it is. This is a piece of quartz, just like some of the other quartz I have. Here's calcite. A lot of minerals like this are considered to have a glassy luster. And so they look more or less like a piece of glass. And that kind of luster is really not all that helpful. However, sometimes you get to things like this, like the galena that I showed you, and it has a metallic luster. And you look at it and say, ooh, it looks like the luster of a metal. And that kind of luster can be helpful in identifying. There are other lusters. There's what they call an adamantine luster. And so minerals that often have real high refractive index will be said to have an adamantine luster. It makes them look like greasy even when they're dry. A diamond is one that has this characteristic greasy kind of look even when it's dry and clean. So luster is another one. There's also a pearly luster. There's a few minerals that have a kind of a pearly look to them. That also can be helpful in identifying them. But again, it's only so many of the minerals have what they call a glassy luster that it's just not all that useful as a clue. Our next mineral clue is magnetism. This is a dark colored mineral. It's kind of heavy. Again, one of many minerals that are black or nearly black. Heaviness tells you something, but one thing about it, the magnet sticks to it, you know that it's magnetite, which is an important ore of iron. See, the magnet sticks to it pretty good. So not a lot of minerals are magnetic. There's only really a few. But if you do have a mineral that's magnetic, then you pretty well know what it is. There's only a few that are magnetic. It's one of the tests that can be done to differentiate between hematite, which is also a blackish, dark colored iron mineral. So it will identify a lot, and it's heavy. It'll identify a lot with magnetite, but hematite is not very magnetic. You can't stick a magnet to it easily like that. So anyway, magnetite, another mineral. It has and the very name magnetite goes along with the magnetism. So our last in this series of identification clues that'll tell you what a mineral is the chemical tests. Now there's certain reactions, chemical reactions that you can do, some of them pretty easy, some of them a little more difficult, that you can use to identify one mineral from another. Now this is just a little eyedropper that I have, and this is that piece of calcite that I showed you earlier. And now I'm not going to do this because it would actually, it would be difficult for me to get it on film such that you could see it and it would make a difference. But if this were filled with hydrochloric acid or some other fairly strong acid, and you put that on the calcite crystal, the little drop of acid on the crystal would start to bubble and fizz and go up basically, as the carbon dioxide gets, that's what happens because it's a carbonate, and you put acid on it. It's basically similar to what happens when you open a can of Coke or 7-Up or something like that. It fizzes. And so a drop of acid on that will tell you. There are related minerals, and sometimes you can differentiate between them using the chemical test different ways. There's a mineral called dolomite, which is a similar carbonate, but a little bit less reactive. And so if you put acid on dolomite, it won't react. But if you take a pin and scratch it up and make a little powder and then put the acid on the powder, then it will fizz. The powder will fizz. So that can tell you the difference between calcite and dolomite. Other minerals like this, I showed you this dark blue copper mineral called azurite. It's a carbonate also, and if you put acid on it, it also will fizz. So those are a couple of easy chemical tests that you can do that help differentiate carbonate. But there are tests to determine the presence of silver or the presence of copper or other things that you can do in mineral tests that will help determine the actual makeup of the mineral, the metals or whatever that might be inside the mineral. So that's what chemical tests are used for. And ultimately, you can do an analytical assay on a mineral, and the chemist can tell you what elements are in that mineral, and then you can use that knowledge to figure out what the mineral is. But normally in field identification, you're not going to go through much more than a basic ID, although a lot of field tests do include that little bit of acid with an eyedropper, because it can tell you limestone, because limestone is made of calcite. So sometimes some of these tests are included in a basic field test. So I talked a little bit about chemical testing of minerals to determine what they are. And so I thought I'd talk a little bit about the mineral classification of minerals based on their chemistry. So, all different minerals will fit into one of these chemical categories. And so I thought I'd talk about it. First of all, I've got native elements, and these are basically minerals that consist of one element. Most common that you'd think of is either a diamond, which consists of carbon, or a gold, which native gold, metallic gold, but also metallic silver, metallic copper. These are minerals that consist of one element only. Next, sulfides. Sulfides are combinations usually of various metals with sulfur, and a lot of ores have significant sulfides in them. Silver ores are full of various different sulfides. Silver sulfide, which is canthite or argentite in some older publications, but also the ruby silvers, polybasite, and all kinds of other combination metals that are combinations of metals and sulfur. The same true for lead, which the main mineral is galena, lead sulfide. Zinc, the main mineral is sphalerite, the zinc sulfide. Copper, there's various copper sulfides. So a lot of metals are mined and processed from their sulfide. The ores are sulfide ores. Sulfates is the next category. It's a different category of rock. This sulfates, instead of just sulfur, it's sulfur and oxygen, which makes the sulfate ion. And probably the most common one in that category is gypsum. Next, we have the oxides, and oxides also are common in a lot of ores. Most iron ores are various iron oxide type minerals. Hematite or magnetite, these are combinations of iron and oxygen. So oxide minerals, and technically quartz is an oxide mineral too, because it's a combination of silicon and oxygen. Then the halide minerals, these are combinations of different metals with the halide elements, which are fluorine, chlorine, bromine, and iodine. The most common one that you see, and it occurs in a lot of ores, is fluorite. It's a calcium and fluorine. So there's the halides. Carbonates are the carbonate group with various metals, and the most common of which is calcite, which is calcium carbonate. And then phosphates, this is the source of phosphate that's used for fertilizer and that sort of thing. And calcium phosphate in the form of apatite or some other calcium phosphate minerals are, the big source for this. Now, finally, we get down to this number 8, and it's like basically this should be number 1, really, because silicates are the vast majority of all minerals that you would find. Pretty much all the rock-forming minerals, feldspars and micas, etc., are silicates. A lot of gem minerals, not all of them, but some of them are silicates, like tourmaline or beryl, which is emerald, are silicates. And, so the number of silicate minerals is huge. In fact, honestly, it's more than all the rest of these combined. And then finally, we'll take a look at tungstates, which is a combination of tungsten oxide and other materials. And probably the most common one of that is scheelite, which is a calcium tungstate. So that's just a brief, quick survey of classifying minerals by their chemistry. And so when you're doing chemical tests, knowing what classification that you're testing for the combination of different minerals, it helps you be a little bit more understanding in what you might be doing. Although this video is mostly about minerals, I thought I'd talk a little bit about rocks. Rocks are basically gatherings of minerals or agglomerations of different minerals that go into, and some rocks are mostly one mineral with very little other things, but there's a lot of rocks that have a number of different minerals all mixed together or, glued together or agglomerated together. And so I talk about the basic ones and we'll take a look at some examples. So the first one we're going to talk about is igneous rocks. Now, igneous means that it's a rock that's been melted. If it's been completely melted, it's going to be an igneous rock. And we basically have two main kinds, extrusive and intrusive. The extrusive rock, igneous rock, is stuff that's come onto the surface as a lava and of course cools very, very quickly and it doesn't have a chance to grow crystals that are more than microscopic kinds of sizes. And so volcanic rocks, this is what we're talking about, volcanic rocks, extrusive, igneous rocks. And we'll take a look at that in a minute. And then intrusive igneous rocks are rocks that have a chance. They come maybe completely molten deep within the earth, but they rise, but they never get really onto the surface. They just come close enough to the surface that they have a chance to cool slowly. And they may cool over thousands or even millions of years. And that gives them the time to grow easily visible crystals that you can see just by looking at the rock. And so that's our difference between igneous, extrusive, and intrusive. So let's take a closer look at igneous rocks.
Now, igneous extrusive rocks are what people think of when they think of volcanoes. A material that comes to the surface and, of course, red hot rock when it reaches the surface cools off really very quickly. And you get volcanic rocks that we recognize. These types of rocks include things like basalt, which this is a piece of basalt from the big island of Hawaii. There's holes in it because it cooled so quickly it didn't have a chance for the gas to actually even escape. This is a very dark colored rock, but the crystals in it are so small you'd need a microscope to see them. Other volcanic rocks are light colored, like this piece of rhyolite. Now, to really distinguish between all the different categories of volcanic rock, you really need a microscope and to take a thin section of the rock and put it under magnification so that you can see what minerals are there, and then that defines what kind of volcanic rock it is. If the molten rock never actually reaches the surface, but just comes close enough to cool slowly over time, well then it gives chance for crystals to grow like this, and you get this, which is a rock called granite. And you can see that it's mostly light colored minerals, and that's typical for granite, although it, again, like the volcanic rocks, you have to actually analyze what minerals are present to say for certain what type of rock it is. Now here's a rock that cooled slowly like the granite, but it's mostly dark colored minerals. This is a rock called gabbro, and it's the slow cooling equivalent of the basalt we looked at earlier, whereas the granite is the slow cooling equivalent of the rhyolite, the light colored rhyolite we looked at previously.
The next type we're going to talk about is sedimentary rocks, and these are rocks that are formed by the breakdown of other rocks. So if it's erosion or even chemical leaching, the material comes off of other rocks, and like if you have sand and dirt and even little pebbles and stuff like that come down, and oftentimes sedimentary rocks are in layers because they've washed down and formed in these layers, and if they get buried deeply enough, the sediment will kind of glue together or bake together and become a genuine rock instead of just loose sand or loose silt and dirt and that kind of thing. They'll actually harden by pressure into a solid rock. So let's take a closer look at sedimentary rocks now.
This is a view of a typical sedimentary rock layer system, and you can see there's different layers here that were laid down, and they have a little bit of a different makeup, and so you have different colors and that sort of thing. And this is a typical sedimentary, kind of looks like it probably was a mudstone or a sandstone that's just kind of hardened into a sedimentary rock.
Okay, so finally our third group is metamorphic rocks. Now I should say that if you're looking for gold or silver or other valuable deposits, most of the time, especially gold, is going to be in one type of igneous rock, but it occurs associated with both extrusive or intrusive types, depending on the geology, or metamorphic. You don't find as much gold associated with sedimentary rocks. Yes, that does happen. It's not unknown, but it's less common. Okay, there's a whole lot of sedimentary rock that isn't going to make into any kind of ore. But metamorphic rocks are rocks that were some other kind of rock and have been subjected to heat and pressure so much that it changes the nature of the rock. So, a sedimentary rock that was like a siltstone or a mudstone, it's basically congealed and solidified clay and mud and silt, under heat and pressure can become a different kind of rock and turn into like slate or even to like schist, something like that, because the heat and the pressure, it changes the minerals. It literally, under the heat and pressure, some minerals that aren't stable at low temperatures and low pressures, under the high heat and pressure, other minerals become the more stable forms, and you may get other minerals grow in these rocks. So that's a little bit about metamorphic. Let's take a look at some examples and talk more about it.
So I've showed you this picture before. This is some schist that's been weathered. The silver gray piece on the bottom right is the original rock unweathered. The piece more to the left in the middle is moderately weathered, and then the piece on the upper right, the small piece, is heavily weathered. But it's still the same rock, and the rock originally looked like the silver material that's in the lower right. This is a version of schist with lots of garnet in it. The material was similar to what I just showed you, but it was under so much heat and pressure such that garnet became the most stable mineral, and the minerals that were in the schist reformed and recrystallized to form a whole lot of garnet. Now, this is a lot of garnet for in schist, but it's not unusual that schist will have a little bit of garnet through it. Now, schist is a rock that forms when mudstone or siltstone is exposed to high heat and pressure. But what if you have a volcanic rock? Well, this is greenstone that's been formed from heat and pressure on basalt, like that Hawaiian basalt that we saw. This is the same kind of material, only these four pieces are from four very different locations. One is from Northern California, another from northern Arizona. That's the top two pieces. And then the lower two pieces, one is from Western Australia and the other is from Western Africa. But all four of these pieces were associated with gold deposits. There were gold that was found near these greenstone type materials. And this greenstone is associated with gold in many cases, although not always. But greenstone belts are a common place for significant gold occurrences. So now that we've learned all this material, let's take a look at putting it all together and integrating it and getting you set up so that you can identify minerals in the field.
So one of the things I want to talk about is that field identification of minerals is not always easy. You know, when you're out there in the field looking at stuff, even if you're an experienced geologist, you know, some minerals can be harder to identify than you might expect. One of the things that's really important is that weathering can make minerals really hard to identify. Weathering can change the hardness, change the color, obscure or even change the luster. And when you change all the clues that tell you what a mineral is, well, that's going to be pretty hard. Minerals are often converted in the weathering process to clay, and like I say, that changes their hardness. They can even be converted to other minerals. I showed you earlier a chunk of pyrite that had been converted by weathering into iron oxides, like rust. And it'd been converted just by a natural process of weathering. So, you know, identification of minerals isn't always easy. Now, I've mentioned a number of times that colors can vary quite a bit. You can have one mineral, but it can come in many different colors. Lumpy or broken pieces of minerals may not show their crystal shape very well. Minerals from the same family, like garnets, can be tough to separate one kind of garnet from another, or one kind of mica from another, one kind of feldspar from another. Field identification is possible in most cases, but it isn't always super easy. And what you know, like I say, makes the difference, and that's why we're doing this course. Now, we've gone over the clues, the identifying characteristics a little bit, but I'll just do a little quick review here. The crystal shape, mineral hardness, mineral density, cleavage. Cleavage is that minerals, a number of them, tend to break along certain planes, and those planes can be very characteristic to help you identify what a mineral is. Now, mineral color, you know, I've said is the weakest of all these clues. It's the most easily visible, and we're going to talk a little bit about streak testing in just a second, because I haven't gone over that. And luster, whether, you know, it has a metallic luster or glassy luster, pearly, adamantine, magnetism, and then chemical tests, of course. There's some you can do in the field, but, you know, the most thorough chemical tests are done in a laboratory by a chemical company that has all the equipment. And unfortunately, the full thorough chemical test can be pretty expensive. So let's do a quick review of this. I have talked some about crystal shape and how characteristic that is. And I just wanted to show you, like for quartz, you know, our upper left-hand side here is a drawing of the classic the shape of a quartz crystal, and I've got a number of examples here, and you can see examples from all over the world. There's some very different examples, all show this same characteristic crystal shape. And one of the things that's about quartz crystals, unless they've been polished or done other things to them as they come out of the ground, you know, you'll see this on the drawing on the upper left. The M faces have lines going across them. There's a series of growth lines, basically, is what those are. As the crystal grows vertically upward, you get these lines on what are the M faces of the crystal. And on all these crystals that I've shown you here, you can see that. Now, in the picture, you can only see it clearly on the lower right-hand one. You can see the growth striations that go across the crystal. But in real life, you can hold quartz crystals if they're of any size, and you can see these, and it helps identify the quartz crystal. Here's a shape, a corundum, which is ruby or sapphire. And you can see it's a hexagonal shape. When you look down the crystal, you get this six-sided shape if you get a good crystal shape, and then usually a fairly flat termination on either end of the crystal. But again, these crystal shapes can tell you a lot. Hardness, of course, each mineral has its own hardness, and you can test for that in the field. I have here my little field test. I kind of showed you this on one of the other videos, but here's a close-up of it, and it's labeled what each mineral is. You can see on the lid, it shows you what things are, and scratching one mineral with another can tell you the hardness of the mineral you're trying to identify, and that can give you some real strong clues. And then this thing includes a little hand lens for seeing crystal shape in crystals that are small, a magnet, some streak plates, and like I said, we're going to talk about streak plates in just a second. The streak plates basically is an idea that you can grind a mineral on a plate and produce a powder, and that way for minerals that are really dark in color, you can kind of tell whether it's really dark brown or really dark green, really dark blue, things like that, and that can be helpful. I talked about cleavage or fracture, and here's some more pictures that help show you this. The green mineral on the upper left is actually the same mineral as the clear mineral on the lower left. Both of these are calcite, and you can see that the angles that the mineral tends to break at when you have a cleavage, that can be characteristic. And so you see in the green the angle of the breakage, and then in the low crystal on the lower left is the same angle of breakage, and that tells you a lot about the mineral. On the right hand side, you see the kind of cubic one with the breakage. That's actually the mineral halite, which is table salt. You could take this, purify it, and grind it all up, and it would be table salt. And it has a cubic breakage. And then on the lower right, you have muscovite mica, which we've talked a little bit about mica and how it tends to break into sheets. Now, I mentioned a streak, and here's a really dark mineral, and someone has given it a streak across the plate, and you see the powder there is kind of a brown color. And this is what you get out of streaking minerals like this. You can tell, and instead of just, it's black or really dark, looking at the powder can give you a clue as to what the actual color is. So what is a mineral? A mineral is a substance that meets the following 5 criteria. It must be naturally occurring, meaning, things that are made by man are not really minerals. So tungsten carbide, which is a hard material, lately they've been using it for wedding rings. My son's wedding ring is made out of tungsten carbide. It's not naturally occurring. It's a man-made product, so it's not a mineral. Inorganic, so something like coal, which is a product of trees and that sort of thing compressed down. Coal is not a mineral. It must be solid, so water, like the ocean, isn't a mineral. It has a definite chemical composition. It can't just be a mixture of things. It has to have some kind of fixed chemistry, and then an ordered internal structure, which means it has to be crystalline. So something like opal is not a mineral, even though it comes out of the ground, because opal is actually a gel. It's kind of like Jell-O, only made out of inorganic chemicals instead of proteins, which is what real Jell-O is made out of. So let's look at some common minerals. We're going to start off with quartz. And quartz, actually, it's silicon dioxide, or SiO2, 1 silicon and 2 oxygens, and it is probably the most common element on the Earth's surface, because it's made of the 2 most common elements in the Earth's crust. So silicon and oxygen are the 2 most common elements in the crust of the Earth. You put them together and you get quartz. So here's some examples that look wildly different. You can see the quartz crystals that look like I had showed you just earlier, and if you look really closely on the crystal in the back of the crystals, you can see the growth lines that I mentioned earlier. The purple crystals are amethyst. And amethyst is a mineral, a variety of quartz. It's purple colored quartz. The lower right is a piece of vein quartz, which is the kind of vein material that gold occurs in. But I will tell you that there's a whole lot more vein quartz than there is gold-bearing vein quartz, or vein quartz with significant amounts of gold in it. There's just a lot more quartz because it's, like I say, a very, very common mineral. Now, the lower left looks like a big chunk of wood. Well, it's a big chunk of petrified wood from Arizona. And it's a piece of wood that's been mineralized, and over a long period of time of being buried, the wood of the log has been replaced by quartz. And that's what petrified wood is. Now here's some more examples of quartz. You can see the upper left is gold-bearing quartz. And I said gold-bearing quartz is a lot less common than just not gold-bearing quartz. But this is an example of what it looks like with a lot of gold shot through it. Then below is rose quartz. This is a pink quartz. And then on the upper right is what's called a Japan Law twin. This is basically two quartz crystals that grow together at right angles. And this is actually not just a random thing where two crystals just happen to grow together at this angle. This is a standard thing that occurs fairly regular when the atoms of the quartz crystal start growing in certain directions, and in the right conditions they grow at these right angled crystals. And then the lower right is what's called fire agate. That's my favorite form of quartz because it's just a beautiful gemstone, and it's rare and only occurs in a few places, but it's just really, really beautiful. Next we have gold, and the characteristic things of gold are its metallic luster. Of course, it looks like a metal, and then its super high density. Now you would say the yellow color is, and yes, that's true. However, there are shades of gold that have naturally alloyed silver in them, and so you can get gold all the way from the normal bright yellow that you're used to, all the way through pale colors. The one in the upper right here is kind of pale a little bit, but there's ones a lot paler than that. I could have put an example here where it's literally almost just silver color. And in fact, there are a few districts. There's an Oro Blanco district in Arizona that's, Oro Blanco is Spanish for white gold. So it does occur in various shades from yellow to silvery colored, depending on how much silver is alloyed with the gold. There's actually a separate mineral name for the really pale stuff called electrum. And then pyrite, of course, if the crystal is right, you can see the cube shape as in the one on the upper left. The one on the right is cubic also. It's just that the picture that I've got here doesn't really show that as well. If you were able to hold this specimen in your hand, you could see that the crystals were cubic shaped. And then the one on the lower left, the crystals are really small. It would be harder to identify the cubes in that, but I think some of them at least you could identify it if you were able to look at it closely in person. Now here's copper ore, chalcopyrite. This is probably the most important ore of copper, and it looks gold in color and metallic, but it grows in certain crystal shapes and is readily identified. It's a little more brassy and yellow colored than pyrite is normally. Here's some more copper ores. These are oxidized copper ores. This is what happens when you take air and water and have it act over a long period of time on things like the chalcopyrite I just showed you. You eventually produce things like this, which is the green is malachite and the blue is azurite. I mentioned metallic silver, and of course silver by itself sometimes occurs as a mineral, and you can see these strange and weird shapes. I've done a video on silver and silver ores, but this is just a quick look at some examples of metallic silver. Silver ores themselves, you can take a look at these examples. They tend to be dark colored and often sooty kind of looking or earthy. But the thing about that is that there are a lot of other things that tend to be dark or sooty. So, just because of those two doesn't prove that it's a silver ore. You'll need other clues, and this gets back to what I was talking about, where you need a series of clues to help you identify your rocks and minerals. Here's platinum. Again, it's metallic and it's silver colored, but this is much more dense than silver. So if you had a chunk of platinum and a chunk of silver in hand, they're both about the same size, the platinum would be almost twice as heavy as the silver. So platinum is actually a little more dense even than gold. Now, speaking of density, here's a lead ore, a very famous lead ore, galena. It's probably the source of almost all newly mined lead comes from galena, and it has a cubic cleavage and a cubic crystal growth phase. So both the growth of the undisturbed crystals, and if you break them, they both break into a cubic sort of arrangement. It has a high density, and this lead color, this gray color, is kind of characteristic. When you add those all together, that's pretty sure definition, or that will guide you to identify a mineral as galena. Let's take a look at some unusual ores. On the left, we have nickel ores. The garnierite, the green, is an oxidized nickel ore. There are places where this is mined. There's an area in Oregon that was mined for this mineral and produced nickel. And then the lower left is a sulfide, a nickel-bearing sulfur mineral. You can see the kind of metallic luster that it has. And then on the right are cobalt ores. The upper right is a pink-colored ore of cobalt that comes from Nevada. And then on the lower right is a metallic sulfide type ore, and this comes from Canada. Here's some chrome and molybdenum ores. On the left is a dark colored mineral, that's chromite. It's heavy, and it comes in a certain area, certain type of geologic environment, but it's the chief ore of chromium that's used for like chrome-plated bumpers, that sort of thing. And then on the lower left is another mineral. This is a lead and chromium mineral. That's a kind of an unusual thing, but it makes for some interesting specimens. On the right, we have molybdenite, and this is the main ore of molybdenum metal that's used as a special strengthener in some types of steels, that sort of thing. But it's a valuable ore and is mined in a number of places across the world. Here's some manganese ores. And manganese is also another thing that gets added to certain steels to strengthen it. And here you can see some dark and sometimes almost earthy kind of color that it goes with a lot of manganese ores. And then iron ores. Here's magnetite and hematite. And on the right is the magnetite, and on the left is the hematite. And it doesn't always grow in this kind of lumpy, the hematite doesn't grow in this lumpy formation. It doesn't always look that way, but it makes for an interesting specimen when it does. But these are the ores, the chief ores of iron. Now, arsenopyrite is an arsenic-rich pyrite. Instead of being the normal yellow color that you're used to with pyrite, this is usually a much more silvery kind of color due to the high arsenic content. It is commonly associated with gold. The piece on the left there is a little chunk I picked up off of a mine dump in Western Australia, was showing to my companions there with me. And then there's another specimen here on the right. But I've seen some really nice arsenopyrite and gold specimens from the mother lode country of California too. Feldspars are a common rock-forming mineral. You can see some examples here. Different colors, grays, buff and pink colors are pretty common. And then this green one in the lower, the kind of blue-green in the lower left is amazonite, and it makes for some nice mineral specimens. It's not a very common type of feldspar, but there's lots of different feldspar minerals. And then the mica is also another family of minerals. In general, a lot of the lighter colored micas are from the muscovite family. The darker colors, a lot of them are biotite, but there are a lot of other micas. This lavender color in the lower right is lepidolite and is an important ore of lithium. Calcite is a rock-forming mineral that it basically is the main mineral of limestone. And you can see the green and then the doubly refractive crystal on the lower right. I've shown you those already, but these are examples of calcite, which is the main mineral that forms the rock limestone. Fluorite is another important ore. It's actually mined for its fluorine content. It's calcium fluoride is the elements that make up fluorite. And it comes in just a wide variety of colors and often makes some really beautiful crystals. And you can see these examples here. It's the mineral that goes when they put the fluoride in your toothpaste. This is what it comes from. Garnets is another family of gemstones and minerals that used in mineral in a lot of rocks. And you can see an example here that's near black. I have other examples that are kind of orangey brown, and then in the lower right there's a little bit of a green colored. Garnet comes in a wide variety of colors. Here's an example of beryl and emerald. You can see the blue-green is kind of aquamarine. The pink is morganite. The yellow version of it is called helidor, and then there's a raspberry red version of it that comes from Utah. This is all the same mineral. It's called beryl. In the green form, it's called emerald. Of course, diamonds come in a wide variety of shapes and sizes. Generally, there's a diamond shape that you can see best in the lower left-hand side. It occurs in a rock called kimberlite, but it occurs in other rocks as well sometimes. The corundum family, I showed you at the beginning, rubies and sapphires. Here's some examples of really pretty colored ruby and sapphire. It has a characteristic hexagonal shape when you can see the shape. Some, like the upper right, those are natural pieces. It's hard to see the hexagonal shape on those. They're just kind of lumpy, rounded types of mineral occurrences. Tourmaline is another famous gemstone. It's been mined in Southern California and up in the northeast part of the country, in Maine and some of the northeastern states. But it's mined also in Brazil and a lot of other places around the world. Topaz is another famous gemstone, well known, and here's some beautiful crystal examples of it. And then turquoise, one of my favorites. I have some turquoise mines here in the state of Nevada. These are some different examples of turquoise, which is a really beautiful mineral. Now we've looked at some minerals, and let's talk about putting all our clues together, because that's the skill that you use to identify minerals. And like I say, identifying minerals isn't always easy. You need a number of clues to help you solve the puzzle of what this mineral is that you're looking at. And all the clues together combine to give you the information you needed. I told you in the beginning, it's kind of like the old game Wheel of Fortune that they have on the TV, where there's a phrase and then the contestants guess different letters, and eventually letters will appear and fill in the blanks, and eventually it becomes pretty obvious what the phrase or saying or whatever that people are trying to guess. And that's kind of like minerals. You figure out the hardness, you see the color, you look at the crystal shape, you know the association of where the mineral came from, you put these things, different ones all together, cleavages, there's a cleavage, and then that will fill in all the blanks, and eventually you'll be able to guess what mineral it is. Now, don't get frustrated if you find it difficult. Basic mineralogy is a full semester college class. It's, when I took it so many years ago, it was a whole semester, and they talked about all different subjects. And of course, they covered more material because they had a lot more time than I've covered here in this just short introduction. But you've had a basically 1 hour condensation of a 50-hour college course. So I couldn't cover everything. But get reference books and practice. That's the thing. Practice makes perfect, and it's a skill, and just like any other skill, if you practice it, you'll learn to get better. Now, I've recommended various books, and I'm going to show you one in a second here, but there's a book called Dana's Textbook of Mineralogy. It's an old book from actually originally written in the 1800s, but still a lot of really valid, good information. It's not like the science has changed radically since then. And common minerals are still common minerals. And so you can actually search for this, use Google for Dana's Textbook of Mineralogy, and if you look on the thing there, you can find it's a free PDF file, and you can download it, and it has drawings. It's old, so it doesn't have color pictures, but it has drawings and that kind of stuff. And of course, if you do it right, the price is free. So hard to complain about free. Now, let's give you an example of solving a mineral identification puzzle. I actually posted this on my community forum there on YouTube, and this is the thing, and I had people guess, and there were some people that guessed correctly. Now, I'm looking at the clues that I can see in this picture and that I happen to know. The clues, first is that there's this unusual crystal shape. Note that the faces are triangles, and it's a crystal shape that has only 4 faces. The 4 faces come together to make a full 3-dimensional shape, and it's 4 triangles on the surface of this crystal. It's much easier to see that in person than it is in this photograph, but you can still see the triangular crystal shapes. So it's a tetrahedron, which is an unusual crystal shape, but those shapes do exist. It has metallic luster. It was found at a mine that's known for producing copper with some silver. And that clue, those 3 clues, the tetrahedron shape, metallic luster, found at a mine known for copper with some silver, it's tetrahedrite, which is a silver antimony mineral that, like I say, often contains significant amounts of silver. That's the kind of thing that you do to identify a mineral. Now here's one, a sample that I picked up in the spring of 2019, and I was really pleased because it shows us a mineral that's kind of unusual. But there's a number of different minerals here you can see, and I've kind of drawn numbers and put arrows to them so you can see what I'm talking about. Now the first one up at the top there, it's colorless, it has a 7 hardness. I actually could see in the hand specimen with a loop, I could see those horizontal growth lines along the length of the crystal that I've mentioned a couple of times already for quartz. And so that characteristic crystal shape and the growth lines, it pretty much identifies this as being quartz. Number 2. This is kind of an orange-brown. You can see actually the bulk of this mineral specimen is that orange-brown stuff. And I looked at that, and on some of the other parts of the specimen, you can see that it has a dodecahedral, which is a kind of a spherical crystal shape. It has a greater than average density. In fact, if you pick up this whole piece, you'll see it's much heavier than you might have expected it to be. And so greater than average density, and the orange-brown color and the crystal shape, this is garnet. Okay, this is a variety of the garnet family. Number 3, you can see labeled there. There's just a couple of these things in there growing. This is a dark green colored crystal. In this picture, it's hard to see. They look kind of almost blackish to dark green, But in real life, in a hand specimen, you would see real quick, even without any kind of streak test, that this is dark green color. So dark green, a long monoclinic crystal, so that's the crystal shape. It has a 6+ hardness, and although I didn't test the pieces in the picture there, I tested some other pieces on this hand specimen, and it is epidote, which is a mineral that commonly occurs with garnet. So it's a mineral association type of thing where you see garnet. It's not unusual to see epidote. And then the number 4 designated, this is a dark silver metallic. In the picture it looks dark to almost black, but if you're looking at it in a hand specimen, it's clearly dark silver colored. It has a really strong single cleavage and a super soft hardness. I mean, it's super soft, and it is molybdenite, which is the ore of molybdenum, which is actually why I picked up this specimen, because it's molybdenum ore. So that just gives you a few examples of how I look at things and identify things and figure out what minerals are, and that's what I want you to be able to do. So after you've had this introduction, get yourself a book like this. Simon & Schuster's Rocks and Minerals is a good one. It's the one I use, but there's a lot of them out there, and they're all pretty good. They have color pictures, which is the one thing you won't get from Dana's textbook of mineralogy, but it does have the things that tell you, what different hardnesses minerals are, and the crystal shapes and different other examples. And you can take a handbook like this with you in the field. You can throw it in your backpack, and once you get out to some place that you're looking around, it can help you identify things. So I hope you've enjoyed this course, because there are there are thousands of different kinds of minerals, and books like this will help guide you. And I hope that you'll get into being able to identify minerals, and that you'll use a handbook like this, and you'll get out in the field and use your lens to test and maybe hardness tests and that sort of thing, and you'll learn the skill of identifying minerals. It takes time, but you can do this.
Mineral identification is really a valuable skill. And, as I mentioned kind of at the beginning, knowing how to identify indicator minerals is really helpful. Now, indicator minerals aren't always the same depending on what you're looking for. If you're looking for diamonds, you might be looking for one set of indicator minerals. If you're looking for silver, you might be looking for another set of indicator minerals. If you're looking for gold, maybe you're looking for another different set of indicator minerals. And to understand how that all works and the geology of that, especially of gold, I've written a book that covers all that stuff and kind of boils down my decades of experience in going out and finding minerals. And I'm going to tell you a little bit more about my book, because I think my book will be a big help to you. I'm going to tell you a little bit more about it right now. This is my book, Fistful of Gold. It's an encyclopedia of everything you need to know to go out and find gold for yourself. It distills down my 45 years of experience out in the field prospecting, as well as my degree in mine engineering. It's, like I say, an encyclopedia. There's a lot to it. It's over 250,000 words long, hundreds of pages with hundreds of illustrations, teaching you what you need to know about geology, about mining districts, about techniques of finding gold. It covers metal detectors, sluicing, panning, dry washing, high bankers, you name it, it's covered in there. It talks some about platinum and diamonds, but it's mostly about gold, because gold is more widespread. It is not so much a book about where to find gold, but a book about how to find gold. Because even if you have a location where gold was mined in the past and you go out there, well, where should you look to be successful in your prospecting, to find the gold that's there? This is the book that's going to tell you that information. I spent most of 10 years writing this book, so I thought a long time about it. It's got, like I say, lots of information. and lots of illustrations, and I've had results from people who bought it. It's available on Amazon, but I recommend buying it through High Plains Prospectors, and I'll put a link in the description for buying this book through them. They have a better price than Amazon, and I have a special deal that I'll tell you a little bit more about, where you can get a 5% discount from the price even with that. On Amazon, the book rates a 4.7 out of 5, which means that of all the people that have bought it, they've been really highly satisfied, and I think you, if you buy my book, will be just as highly satisfied as well. Now let's talk a little bit more about High Plains Prospectors. They're a prospecting shop, a mail order prospecting shop that I've partnered with. The deal is that I can get you a 5% discount, a coupon code, and I'm going to put the code to that right here. It's just Chris Ralph, all caps with no space between Chris and Ralph. You put that in there as a discount code, and you'll get 5% off their already really good prices. I think it's a great deal where you win by getting a discount, I get a little percentage of that, and they get new business. So if you need prospecting supplies, High Plains is really the way to go. And I'll put information, like I say, in the description more about how you can work with them, because I'm working with them. They really are great guys, a great company. For even more information, I also have a website, and I'm going to show you my webpage and talk a little bit more about that right now.
This is my webpage. It's located at nevadaoutbackgems.com. You can Google it, or I have a link down in the description below. But there's lots of information here, miscellaneous stuff, pictures, some historic information as well, stories. It's got a lot of great fun stuff. You'll probably be interested in it.
Now, on all of my YouTube videos, I encourage you guys to ask questions. If you have thoughts, comments, suggestions for things that I ought to look at in my videos, things that you want to find out more about, and I answer 100% of my questions. There's not very many YouTubers out there that answer 100% of their questions. I'm one of the few. And so I will do my best to answer what you have. I mean, I only can write so much. Sometimes the answer is something where I'm going to recommend that you buy the book and read about it. I also ask that you subscribe to my channel, click the bell notification so that every time I come out with a new video, you'll be able to watch it. And like I say, I cover a huge amount of topics. I also have 250 videos that I've already done. And so you can go back through my catalog of videos on YouTube. I'm sure there'll be many videos there that you'll want to take a look at, especially if you have any interest in gold or platinum, diamonds, gemstones, geology, and that sort of stuff. My YouTube site is going to be right up your alley. So I'll see you again real soon. We'll be out in the field and back in the office at the whiteboard, and whether we're looking at gold or platinum, diamonds, gemstones, or other interesting geology, it's going to be fun. You're going to enjoy it, and we'll see you again real soon.